right. All right, why don't we get started? Okay, welcome back everybody to Python for Physics. If you're new to the class, welcome. If you've been joining us from the beginning, welcome back. For those of you that are new, we're gonna, the stuff that I'll be talking about today is largely detached to everything that you've seen so far. So you can join us, but it will help you to go back and look at the previous videos. For some context, this is a class that I'm co-teaching with Professor Ted Rogers. In the last 3 lectures, he's the one that has been lecturing. Today is going to be me. So today we're going to talk about data analysis and analyzing data broadly. And we might start talking about how to determine masses of particles that we can't see. And so this is going to be tied to the neutrino mass. I might not get to that today, in which case we'll pick that up on Thursday. But before that, let's take care of some administrative stuff. If you're new to the class, and as I've already mentioned, we have tons of information out there for you to catch you up, or even if you've been in the previous classes and you haven't having access to the Dropbox or the chat that we have set up for you, which is Slack. If you want to have access to all that information, what you have to do is write to python4physics@odu.edu, and what you will get is an automatic reply that looks like this. Some of you have not been getting automatic replies, and I can't for the life of me figure out why that's the case. And so I've been just going through and emailing everybody the links one by one. And so the information that you will have there is access to our website. So you can just click this link and that'll give you access to our website. There we're addressing all your frequently asked questions, as well as putting some quotes, some nice stuff that you guys have been saying about our class, which is really heartwarming to hear. Also is useful for other people. And so if you have any other positive things to say, go ahead and you can shoot them on the chat right underneath where you're seeing this, or if you have any constructive feedback, and we've received some constructive feedback in the last couple of days, we take it very seriously, and so we're trying to address your questions. And so also give us constructive feedback. You don't have to always say that we're doing a wonderful job, okay? And then we've also set up a Slack chat so you can talk to the TAs and us, the faculty, and that you will get this link to that. There is one caveat that this Slack chat, Slack only is permitted for people that are 16 years of age or older. We have no mechanism to test your age, and so we're assuming that we're adopting the honor system, and so we're hoping that you will abide to these rules, okay? The live stream link, you've found it because you're on it, right? And then you have the recording links, and so you have access to all the recording material, not just Python for Physics, but the direct Python for Physics recordings are here. And then the last but not least, you have the Dropbox link, okay? So here's our page. This is what it looks like. And we have some administrative information. Also, we're looking for translators in Spanish. We have 4 of you already volunteer, and so we're coordinating with those folks to start translating all this material into Spanish. If people need this to be translated into any other language, let us know. It might be hard for us to accommodate that, but we're trying. We've also gotten some feedback about the captioning. We're looking into that, trying to make the captioning more accurate. So we're working on that. Last, we're going to set up a Dropbox link for you to share your code with us and other people. This, I cannot just send you the link for this to give you permission for you to write into the Dropbox links. So for this, I need your email. So what we need you to do is send us an email saying to give you access to Dropbox links. So maybe just say to the Dropbox folder. So maybe say Dropbox access. Okay. So let's put this so that it's easier for me to read your. So subject, make it Dropbox access. And so this would be a different Dropbox folder than the one that you've been using to see the material, because this would be one that you would have administrative rights for you to write the code into it, okay? And so if you want to share your code with us, and we're going to be posting some different challenges for you to show your programming skills and for us to be able to see more clearly, help you get better. And so this would be a place where you can put that code for us to see. Okay, so that's administrative stuff. And unless, maybe this is a good point to see if you guys have any questions, anybody in the live stream has any questions for us that is pertaining to administrative stuff before we start diving into more fun physics content. So is there any administrative questions so far, folks?
Nothing coming in yet.
Okay, great, awesome. So yeah, if you have any questions, basically just email this email and you'll get everything. Great, so the outline to this week is fairly easy. So we're gonna go into introducing data analysis. We're just gonna walk about the basics, and this is basically what we're gonna cover today, is just how to do data analysis, why it's important, and how to do it in particular within Python. And then I'm gonna give a little bit of introduction into some concepts in particle physics as well as relativity, okay? And this, we're gonna do a little bit of data analysis here, since this is data analysis is the bread and butter of particle physics, okay? And so let's start with a little bit of motivation, as you should always start with any talk. And the question is, why do we need to analyze data or acquire statistics in general? What is, what do we mean by statistics? The motivation is quite simple. Basically, we as physicists or as scientists in general, we construct models and we try to understand which models best describe or best fit the observations that we take of nature. And this is remarkably important, right? Because we can construct an infinite number of models, and these could describe any class of universe. But what we ultimately want to do as scientists is describe the universe that we live in. And so this requires us to observe it, to observe the universe and observe nature. To be able to observe it, what we mean scientifically, what we mean by that is that we need to collect data, we need to have a quantitative way to describe the universe so that we can observe it in a quantitative way. Unfortunately, any tool that we use for collecting data cannot be infinitely precise or infinitely accurate. So everything has a resolution scale, right? And we're familiar with this in the context of rulers, right? There's a minimum length that they can go, after which we can't really resolve them. And this is actually true at the most cutting edge parts of science. There's always some resolution scale that we can't resolve. And so most times in physics, we can never, in addition to this, to the fact that we have to observe nature, and our tools have a maximum resolution scale. As theorists also, most times in physics, we can't always determine quantities exactly. So instead, what we're required to do is perform some sort of approximations to the theories that describe nature. And so this, even in the theoretical world, this requires us to understand how poorly do we really, or how poorly or how good do we really describe nature. So we need to understand what is the error that our theories in solving our theoretical models that we impose in nature, okay? And so these are two important sets of motivations, and we're going to talk about both of them essentially. And so what we're going to learn about first is talk about probability and statistics, so basics of probability. So I'm going to assume that you know essentially nothing, and then we're going to build you up. We're going to try to understand, we're going to understand how to understand and describe data, and we're going to start estimating and calculating statistical and systematic errors, okay? And so statistical will be related to how we, how much data we acquire. So how much statistics do we have? And then the systematics is going to come back to this question that we're always making some sort of approximation in trying to understand nature. And so how far away, what errors do we introduce by making these approximations? And those are going to be tied to systematic errors. So basically, data analysis appears essentially in all of the scientific fields out there. And so I'm going to take a couple examples from fields that are close to my heart. And so as a particle nucleophysicist, these are two perfect examples, and they're both tied to the Large Hadron Collider at CERN. And so on the top right, basically many of the discoveries that we see today in particle physics require detailed data analysis. And whether we see a particle or not, or we see one property of a particle or not, relates tightly to how well we can describe the experimental data and how robust is our analysis of that data. And so let me give you two examples. The first one, perhaps you're very familiar with, which is the Higgs boson. So the Higgs boson was the missing particle of the Standard Model, and it was discovered in 2012 at CERN. And one of the two plots that led to the discovery of the Higgs is this one, which is a CMS analysis of the Higgs to photon decays, and this plot led to the Nobel Prize, which I'm highlighting over here. And this is a data analysis that led to that discovery. And it's easier to zoom in, by subtracting the dropping curve of this data. And what you see is a tiny little bump right here. And you see the data are these black points with these error bars, and it's the fit to this that led to the confirmation that there was indeed a particle there. And so this was the result of the Higgs boson, which led to the Nobel Prize. And so what we're hopefully the next two sets of lectures trying to explain to you is, what does this tiny little bump mean, and how can you, in principle, perform a similar analysis to lead to a similar discovery. And here's another example of pentaquarks, which are different classes of particles, which are made out of not three quarks like the protons and neutrons, but are made out of three quarks and two antiquarks. And so these were discovered for the first time at the LHCb, which is one of the experiments taking place at CERN. And here you can see these bumps correspond to these would-be pentaquarks. And so again, the point that we're going to try to explain to you is how can you perform a similar type of analysis if you were to be working in one of these experiments. And so if you don't know what the Higgs is, let me highlight a couple of things that would be useful. First, there's this little YouTube video, which is quite fun, which explains the role of the Higgs and how it gives mass to other particles like the electron and the quarks. And it's quite intuitive. And so there's a beautiful explanation. So I would point you to that video. Another thing that I'll highlight is that my collaborator, Max Hansen, is going to be giving a talk on July 20th on the experiments that are basically, it's going to be giving a talk about CERN, about the present and future, the past and future of this world's best microscope, which is this particle accelerator. And if you haven't seen an image of CERN, of the LHC, that has an image, and so you can see it's the biggest particle accelerator in the world, and it crosses the border between Switzerland and France. So it's a remarkably powerful machine. And here I'm going to give you one more example where data analysis has led to remarkably important discoveries, or in this case, not discoveries, but rather resolutions to issues. And this is tied to the mass of the proton, to the radius of the proton. So the proton, you can determine properties of it by smashing electrons into it. And in particular, by smashing electrons into it, the proton and the electron emit photons with each other. And this photon can probe the structure of the proton and can lead to determinations, among other things, its radius, its charge radius. And so this is right here experimental data of this process. So it's a reaction for a proton and an electron to interact with each other, where you end up having a proton at the end. And this is experimental data. And this is determined in terms of one of the many different kinematic variables that describes this reaction. And from experimental analysis of this data, people were able to determine the radius of the proton. And perhaps you might have heard that there was a lot of controversy by different ways to probe the proton radius that led to different determination. And it turns out that this has been resolved. And there was many controversies about the question of whether perhaps the proton itself had different radius depending on how you probe it. But it turned out that all the experiments have led to a similar determination of the proton size, and the resolution was how the data was analyzed from the different experiments. And so again, data analysis was remarkably important to, in this case, resolve a long-standing puzzle. And this title is very dramatic. It's a little dramatic, suggesting that hope dies, meaning that if it wasn't this resolution of data analysis, then there would have been new physics. But I think actually this is a lot more hopeful, because it's suggesting that we do understand nature, and we can understand different phenomena that are taking place in different experiment labs, or in different labs with remarkable accuracy. And then the last point that I'll make is that data analysis is not just important for experimentalists, but it's also important in how we analyze theoretical calculations. So here, what I'm showing you is a calculation that you will get to play with. So each one of these points is a determination of the mass of the proton as a function of the parameters of the standard model. And what you're seeing here is that these different groups have determined this mass of the proton using different input parameters for the standard model, meaning we're playing with different universes where the Higgs, let's say, has a different contribution to the mass of the quarks. And so by doing this, we determine different proton masses. And you can see that there's some trajectory, there's some trend in all this data. And so towards the end of this next 2-week series, you're going to be able to analyze this data and be able to say how, what best describes the behavior of this. Okay. So to summarize, data analysis is remarkably important in experiments. It's also important in our theoretical studies. And so we're going to jump into understanding the basics of data analysis. And we're going to start applying some of this and start coding up in some different examples towards the end of today. So that's it for my motivation. So why don't we start with playing some simple ideas of probability, so that this is going to be foundational for everything else that we're going to do. Okay. So let me start by asking some simple questions. Let's imagine that right now, I don't know how many of you guys are seeing this video, but let's imagine that I had access to everybody. And so let me ask, if I were to randomly select one of you, what would be the probability that if I pick one of you, that you would be a woman, that you would be female? Well, the answer to this, we know how to quantify it. The probability would be, let me just grab the total number of you that are women and put you on one side. And then I'm going to grab everybody together, including all women and everybody else. And this will be the total number of people. And so the probability that I pick out somebody randomly, and that person to be a woman, it would be the fraction of women to the total number of people. Okay? This would be this fraction. And always it has to be bounded by 1. So it'd be it can't be bigger than 1, right? Because there's never going to be more women than total people in the room. But it can be 0, right? So it could be no women, and everybody else would be, then this number will be 0 on top. But it can go, so it's always bounded from 1 to 0. Okay. So instead, let me ask a different question, and the question would be: what if I randomly pick a person from the room? What is the probability that that person is a high school student? Well, it's the same exercise, right? All I have to do is just grab everybody and then count those that are high school students. And so I would just grab the total number of high school students and divide it by the total number of people. And so that would give me, again, the probability that the person in the streaming session is a high school student. Next, I can ask a different question, which is, what is the probability that if I pick a random person, that person is both a woman and a high school student? And so again, then I just do a more selective sampling, which says, what is the number of total female high school students? And I grab that number and I divide it by the total number of students. That again So that would be the probability of women that are high school students. It would be bounded by 1, but it also would have to be bounded by the number of women and the number of students, or high school students, because this number is a subset of the larger of both, is the cross section of both women and high school students. And so from above, it's always going to be bounded by this, but also it's going to be bounded by 1, and from below is always going to be bounded by 0. Okay? And so that's how we can do sampling, right? And where statistics starts to buy you quite a bit is when I start asking harder questions. And so now here, this is quite intuitive as far as probability goes, right? And how do we, assess these random numbers in finite sets group of people. But now let me start asking questions, not about the people that we have in our class, but rather about populations, just bigger populations. And so let me ask a different question, which is, what is the probability that if I pick a random person on the street, that person would be a female high school student? That's a much harder question, right? And so even answering the question, how do we go about setting, here, this is a question that we can't ever reach to, 100% accuracy, but we can try to estimate the answer to this question. And so one good way to estimate this, I would let you guess, but right now I can't hear you, so I'm gonna guess for you. So here's a good guess, which is I could just go to Hampton Road, which is the road where Old Dominion is at. So this is the road right here, is Hampton Road. So I could go to Hampton Road and start asking people randomly if they're a female high school student. It's a little bit of a weird question, right? They might look me a little funny, but I could do that, right? And then I just tally the no's, meaning I just write down the no's, right? And then I tally the yes, meaning I just write down the yes, right? And so then for a finite amount of sampling, I can just calculate the ratio of yeses versus the total number of people I've asked, which is all the no's and yeses. And in the limit where the number below becomes really large, so in the limit that I ask everybody, then I would get a good estimate, or in fact, I would get the right estimate. So if I ask everybody, then I would get the correct answer, which is the probability of me randomly picking a person on the street to be a female high school student, okay? This is impractical, right? And so we can't ever do this, right? And this is the basic idea of polling and how we do analysis of, cases of diseases or anything else in some population. We can't ever really do this, right? And so this is very impractical. And in fact, for every question that I would want to ask, right, I fixated on the fact that I'm asking people if they're a high school student, but I could have asked any other question, right? If they have blue eyes or black eyes or anything, right? And so for every single question that I would want to ask, I would essentially have to grab an infinite amount of data. And this seems remarkably impractical, right? We can't get anywhere with that. And so to give you insight that there's got to be a better solution to this, I think it's useful to look at an anecdote. So here's an anecdote from 1906, where a statistician the statistician appeared in a livestock fair. What is a livestock fair? I don't actually know, but I think it's a fair where people are showing their livestock, right? So they're showing oxes, cows, etc., right? And I'm a city person, so that shows my ignorance. And so they go to a livestock fair. The statistician appears in a livestock fair, and there's an ox in the fair, and the ox is in display. And the villagers, so people in the village, are invited to guess the animal's weight. And you can guess that, okay, if you're really good with oxes, perhaps you can get a good estimate, but in reality, nobody really knows the weight of the ox, right? this is not interesting. The interesting thing is that approximately 800 people participated, and so they just guessed the weight. And then the statistician afterward decided to look at the data, and so the statistician had access to the 800 responses, and then calculated the mean of the distribution. So there was a random set of numbers. They're not random. They're distributed, and the statistician calculated the mean of the weight of the ox, as guessed by the people, which had no real information other than sight of the ox, and found that the weight was 1,207 pounds, which was within 1% of the ox's actual weight. That is remarkable, right? The people asking the question, the people guessing, had no idea what the ox really looked like, and no one person got it right. Nobody got it right. But just from asking randomly people, you get the weight to within a percent error. And so this suggests that there has to be a smarter way for us to understand and estimate quantities without having to do, and notice, it only took 800 people, right? We didn't have to ask millions of people to get a good accuracy. And you didn't have to ask experts either. These are just villagers. And so there has to be a way for us to get at estimates that are much more accurate with smarter ways. And so this is the idea of statistics and why it's useful to try to determine averages and other quantities. And so to do that, what we're going to do is determine distributions of data, and we're going to take averages of those data, and we're going to display them using histograms. Maybe this is a good point for me to stop, see if there's any questions before we start switching gears a little bit.
No questions yet. I do believe there is a little bit of a delay on the feed, so just watch out for that.
Okay, sounds good. How does that affect me?
I think questions might just come in a little delayed from when you ask.
Okay, sounds good. Also, if there's no questions, that's fine. We can just continue. I just want to make sure if there's a need for us to stop, we can stop.
No questions yet.
Awesome. Sounds good. Okay, so now let's start quantifying all these ideas and start applying them into writing our own code. Okay, so let me start thinking about distributions and start plotting data in histograms, using histograms. And you probably have seen this, and so it's just useful to give you a little, to refresh, even if you have seen it. So let's imagine that instead I wanted to determine the height of the average American. And so what I can do is just go to the street, right, and start asking a random assortment of people. And so imagine that I have 100 people, and I separate them. I ask 100 women and 100 men. I could ask both 100 men, 100 people, both women and men, and we get some distribution that is peaked around somewhere in the middle of the two. Okay, but here I've separated them by gender, just because on average we know that women are a little shorter than men. And so in a sample of 100 random people, this is roughly what I would get. And here the histograms, so these plots that you're seeing, perhaps let me zoom in a little bit because maybe the numbering system is not so clear. And so what you're seeing on the bottom, and this is the types of plots that we're going to be playing around with quite a bit, and you're going to be making some of these towards the end of today. So on the bottom, what you see is the height in inches, because we're in the United States, and I prepared this for people that know about inches, but not centimeters. And centimeters, inches is approximately 2.2, right? No, it's around 2 centimeters. It's around 2 centimeters, okay? So you can multiply this roughly by 2, and you would get, the height in centimeters. And so within this sample, I managed to get some people that are, very tall, comparable to LeBron James, who is roughly 6 feet 8 inches. So he's a famous basketball player. And then on the women's side, I find, people of all sorts of different heights. I don't get somebody as high as LeBron James as women, but I have several people. And just for scale, if you know Megan Rapinoe, she's a famous soccer player in the U.S. team. She's somewhere around here. So that gives you a sense of scale, okay? And you see it looks a little bit of scatter. And so what I should have said, let me highlight it a little bit more. So on the x-axis, so on the horizontal axis, you see the height in inches. And then on the top, what you see is the number of people, okay? And so here, for example, in this number right here, I have a little bar that is centered, that hits 1. So that tells me I found one person of this height, okay? Here, I have a little height that is at 3. And so that means that I found 3 people of this height, which is, I think, this is 60, 61, 62. So I found 3 people that are 62 in height. Okay, and you see that this distribution. The distribution is just the number of events that I'm measuring for each value of the horizontal axis. And so you see that I'm measuring here about, what is that, 13 or 14? 13 number of people around this height, okay? And you see that there's, these distributions are somewhat random, but they seem to follow some sort of, there's a close to a peak somewhere towards the middle, and then they have little tails on both sides. And so let's go back to the display mode. And so now let me start sampling not 100 people, but instead 1,000 people. And what you start seeing is that things start to align and look a little smoother, right? You have less jaggedy spots. You have no essentially empty spots. So here you have one point where you have a single person, but it starts to look a little smoother. And so if you start now looking not 1,000 people, but we multiply that by 10, so we start having 10,000, you start to seeing a very uniform distribution. And for you guys, for you out there that are fans of Game of Thrones, there's Gwendolyn Christie, who's quite an outlier in as far as the female height. She's very tall, and so she's you can imagine that hiring an actor that is that tall is like finding somebody in 1,000, right? In 10,000, right? So it takes about 10,000 to find somebody that tall. So she's quite an outlier. And so what you're seeing, right, is that as a function of time, the more samples I make, the more smooth these distributions look like, and they kind of start looking like a bell, right? And this is what is referred to as a bell curve distribution, or a Gaussian distribution, or a normal distribution. They're all the same thing. And so I'm going to be introducing this in a second. But first, why don't we start playing? No, we're not going to play just yet. We'll play in a second. But first, let me start introducing some quantitative ways for us to describe these distributions. So,
real quick.
Yeah,
real quick. We had a good question from J. Liu Chao from Chiayi, Taiwan. He asks, how do theorists use data analysis if the main job is to predict?
Yeah, that's great. So there's two classes of theorists. There's many classes of theorists, but there's some theories that, for example, will determine some mathematical equation that describes experimental data. And a lot of times, and in fact, at Jefferson Lab, we have a good portion of our group within Jefferson Lab, within the theory group, not only derives mathematical equations, but then proceeds to uses these mathematical expressions to fit experimental data. So they might be able to do their own analysis of experimental data, even though they were not partly responsible for acquiring the experimental data. And a lot of times, the lines, there's collaborations that include experimentalists and theorists. And so it's not unheard of that some theorists will work with experimentalists, as well as, the flip side, there's experimentalists who do theoretical work, right? You don't have to do just one or the other. So there's people like that. These are results that have been obtained from theoretical techniques using statistical estimates of physical observables. And so these are, these points, which have a mean value and an uncertainty, were all acquired using theoretical techniques. And to obtain them, it was required to do some data analysis. And on top of that, what we're going to see is that if I want to describe all of these, I can by performing some data analysis. And in fact, you're going to be performing a data analysis of this. And so data analysis appears in theory all the time. I do some data analysis quite often. In fact, my students and Alex has been doing some sort of data analysis, some toy model data analysis in his most recent work. And so data analysis is not just for experimentalists, but also for theorists. Okay, should I move on?
You're good to go.
Awesome. Okay, so I've already introduced, at least in words, the idea of a mean or an average. And I'm sure most of you are familiar with this. The average is just the point that is essentially at the middle of any distribution, right? It's if you have a distribution that is perfectly centered, and it depends on which distribution we're going to talk about, but here we're going to assume only bell curve distributions or Gaussian distributions, which this is going to be the case. So imagine, let me define the average rigorously. So imagine that I have a distribution with n data points, okay? And we're going to use this symbol, which means that the xi, so this is going to be my data set, is within braces, and this set is going to be open braces, elements x1, x2, This ellipsis just means x3, x4, and so forth, all the way to xn. And there's going to be some integer, okay? I don't have to, for this, I don't have to assume what value n takes. It could be, in this case, it has to be greater than 2. That's all, right? So it could be 3, it could be 4, and so forth. And so we'll play with some examples. In fact, we have some examples right here, okay? And so the average height, imagine that I have a distribution of n data points corresponding to heights, which is x. Then the average height is just going to be the sum over all heights divided by the number of measurements, okay? And this makes sense. This is just taking the point that is like at the middle of all the possible heights, right? And so all I have to do in this case is just sum all the xi's from 1 all the way to n, and this is what that symbol means. The sigma is a Greek letter. This sigma is capital sigma, which is a capital Greek letter S, essentially, which stands for sum. And so I'm summing xi from 1 to n, and then I'm dividing by n, the number of elements. And so literally this means x1 plus x2 and so forth, all the way plus xn divided all by n. Okay? And so you can use some simple examples. Let's say my data is just 2 points, 55 and 60, and I ask you, what is the average? Then you grab 55 plus 60 divided by 2, 57.7, right? And it's just a point that is right in between the two. Makes sense. If I have 3 points, then I just do the same thing, right? I got 55 plus 68 plus 60, all divided by 3, the number of data points. And I get 61. Easy enough, right? Okay, the thing that starts to then be slightly less easy is the standard deviation. So a standard deviation is a measure that tells you the spread of the distribution. It's telling you how far is the distribution really tight, meaning everybody's really close to the mean, or is it very spread out? And so that's what the standard deviation is telling you. And it's defined as essentially the distance away from the mean. Okay, so you're measuring the distance away from the mean. You're squaring that, but eventually we're going to take a square root, okay? So this is just assuring that this number is positive, okay? So you're summing over positive numbers, and then you're dividing by the number of points, and you're subtracting 1, because you already included into the definition the average of the distribution. And so this makes sense. If I had 1, let's say I had only 1 data point, right? Then I would be dividing by 1 minus 1, which is 0, and so that would give me infinity. And so the definition of the standard deviation is already telling me that 1 is not a well-defined data set, or in other words, the uncertainty, my distribution would be infinitely large. Okay, so all distributions that we'll be considering are so-called normal distributions or Gaussian distributions. And so I would point you to the Wikipedia page for normal distributions. And these are distributed according to the probability density of this kind. So it's an exponential that is centered around, let's zoom in. Let's look at this. In fact, let me see. Maybe I won't use it yet, but I will bring up my iPad so that we can use it if needed. Oh, of course, I forgot my cable. Oh, I didn't. Good. Okay, so it's a distribution that is centered around 0. And you can see here, sigma is a standard deviation defined above, which is a positive number. It's always positive. And so I'm taking an exponential exponential minus a positive number. In other words, the thing that is inside exponential is always negative. And so exponentials are, if the argument of the exponential is negative, they're always decaying, and they're peaked when the argument is equal to 0, right? And so the maximum value that this can take is when the argument is equal to 0, which is when x is equal to x bar. X bar, just to remind you, I'm always going to use this notation where x bar is the mean, okay? And so when x is equal to x bar, the argument of the exponential is 0, and any number to the 0th power is equal to 1. Then I have to divide by this amplitude, this number, right? But this is going to be peaked when x is equal to the mean. Away from it is going to be decaying off exponentially, exponential to x minus x bar squared. And so there's what the distribution looks like right here on the bottom. So here's a little picture of Gaussian distributions, which look like the distributions that I showed you already. And one important way to think about the definition of one standard deviation, which is a lot of times what we're showing, what we'll show is the mean value as a little point, and then we'll add a sigma and subtract a sigma, and that's what is going to be shown by bars. And so that might be useful for me to show my iPad. So give me a second while I'll connect my iPad, and I'll let the guys see if there's any questions. Okay. Good. Can you see the iPad?
Yep.
Awesome. And so a lot of times what we'll be showing is, let's say that I have sometimes we'll be showing some function of y, which is a function of x. And we'll be showing it has some particular value. Let's say that this I measure at x naught, I determine a value y naught, okay? And so this is x naught over here. This is y naught. That's nothing new, okay? But sometimes what we'll display, what here is going to be displayed, let's use the notation that I'm already introducing. Let's say that I, let me put bars everywhere, suggesting that I've determined some statistical estimate of this function at that point, okay? And what we'll show are error bars along the y-axis. And what this means is at this point, let me use a different color. This point is equal to y naught plus sigma of y. And this point right here is going to be y naught minus sigma of y. And so what this really means is that there's some distribution. I've determined some sort of distribution of this data, and it has a behavior like this. Oh, now you're going to be judging my drawing skills. I promise you I can draw. Okay? So it means that this data on the y-axis, is distributed like this. And if you look into the slides, the sigma is telling you that 68% of the information is encoded between 1 sigma above and 1 sigma below. Okay? So that tells me that this region over here tells me about approximately 68% of where my value of this function was obtained. Okay? And in fact, you will see sometimes that I don't only have errors along the y-axis, but I also have them along the x-axis. Because I've determined my function at some finite value, that this, my x-axis will also have some uncertainty. What do I want to call it? Sigma x. Okay? So these are, I will refer to these kinds of plots as error bar plots, because they look like little bars that correspond to errors. And Python actually refers to these as error bar. Okay? The other kinds of plots that you've been seeing are histogram plots. And so these are they just show you, the distribution of points. And here it's telling you the number of events within this region, within some region of X. Okay? All right. And so it's going to be useful to display the uncertainties of these distributions in just a second. So here, using this definition, you can just code this up for different distributions, and you can calculate not just the mean, but also the error, and you're going to start doing that just shortly. And so for a given distribution, here I'm asking height, I think this is for men, I can't remember, or women. Women on top, of 100 or 1,000 people, and you're seeing that my distribution starts to peak around mean value. I just calculated the mean value, and this is what I got, this line right here. And then I grab my mean value plus 1 sigma, my mean value minus 1 sigma. You see that indeed most of the events are inside of this these two columns. And if I make this bigger and bigger, 10,000 or 100,000 or a million, you see that the distribution becomes beautiful and Gaussian. Okay, this is a good place to stop. See if there's any questions, and if not, I'll just continue through. Basically, this is where I start asking questions out of you, if you don't ask questions out of me.
Raúl.
Yeah, Juan.
Hello. Well, we have here a very question from Chennai, India. He asked, what other fields in physics use a lot of statistics?
Other fields in physics?
Yes.
Oh, I mean, it's important in all fields of physics. Condensed matter, atomic optics, anywhere where you're taking data, you're always going to be obtaining data with some amount of samples. And so then always you're going to have to analyze that data compared to some mathematical expression that describes the data best. And so you're going to have to do some sort of fitting and optimization of parameters. And we're going to learn that shortly. So we're going to, not this week, but next week we will start doing fits to data of different kind. And so it's important in every experimental field and in some theoretical fields. All right, should we go on? All right, so here's a question for you. And we're going to do this together. And so I would encourage you to start doing this on your own, trying to find a solution. I'll give you a couple minutes, and then we'll start working through one together. And what I'm doing here is that I'm giving you a set of points, and you have to calculate the average of these sets of points of this data and the standard deviation. Of course, you could do this with pen and paper, right? But this class is not called pen and paper for physics, right? It's called Python for physics. And so what you're being asked to do is use Python to plug in these numbers and then calculate the average and the mean. And so you can try to figure out any which way you want. And in a second, I'll show you some tools that will make your life easier. So here's what you're going to do. In the meantime, I'll start ramping up unless somebody else wants to do it. Somebody wants to show how to calculate this using functions in NumPy. I don't see any volunteers screaming out. All right, so let me start showing you some tips. So here, I've just copied and pasted this data, so I can do it again. So if you haven't seen this, I think you've been seeing Ted use Jupyter, but I can use the terminal. So this is just this is IPython, which I've mentioned before. It automatically built in NumPy and Matplotlib and other functions. And so I don't have to call it NumPy. I don't have to define it. In fact, I didn't have to put that NP there, but I can. And so there's different things that I can use. So in fact, NumPy, so let me just for clarity, import NumPy as NP. I don't have to do it, but I can do it. Okay. So NumPy has different functions already built in. And so the first one is the mean, which will calculate the mean of this. And so I get that the mean is 6.3, so 63.33 repeating, okay? I could also get the length of x, and this I think is built into NumPy. And so the length of x is going to give me exactly what you think is going to give me. It's going to give me the length of this array. So I've defined an array, which is a vector for some of you that are familiar with vectors, but it's just is a list of points, and it acts as a vector. And so it has 1, 2, 3, 4, 5, 6 components. And so the length of x, well, it's not in NumPy. I lied. I think it's not in NumPy. So it's just x, 6, which is the number of elements inside of our. Okay. Then there's another function called sum, and I'll let you guess what this does. It just sums all the elements inside of the array. So here's an example. Let me sum 1 plus 1. You see, sum is just adding all the elements inside of the array. I could use, in this case, I defined it as a list. I can define it as an array. Either way, sum works for both. Okay? And so let me take the sum of x and divide it by the length. Let me make it a float just in case. By the length of x. And you see that I got 63.33, which is exactly what I got before for the mean. And good, because that's the definition of the mean, right? This is the mean is just a sum of all the elements divided by the number of elements. And so I got the same answer. Good. Instead of coding up the standard deviation, I'm going to use a NumPy function. And you can code up your own standard deviation. And I would always encourage you to do so in case that you don't understand the definition of the functions that are built into Python. Also, cross-check Python. You should always cross-check as much as you can, okay? And so there's a standard deviation tool, which what it does is that it takes a standard deviation of some array, in this case x, and there's a flag to it, which is DDOF. And what it's doing is that it's shifting this number n by some number. And so in this case, I'm saying that number to be 1. And so this automatically calculates the standard deviation, which is 26.1, etc. Okay? And this is what I got over here. So I just calculated the average. I got 380 divided by 6, and that's what I calculated. The standard deviation, I just took the definition of the standard deviation, which is a sum of the value of x minus the mean squared plus the next one squared plus etc., all divided by 6 minus 1, which is 5. And I took the square root of everything, and this is the number that I got. And I rounded it down, right? Like I rounded the 1 and the 3. Okay? And so you're going to start playing with this, and we're close to maybe a good stopping point. Juan, you have a question?
Yes, actually, I have two. The first one is the following. Is from Pratiksan Sarma in India. Asking, hi, can you explain again why you consider n minus 1 and not n when calculating the standard deviation?
Yeah, so this is I'm taking the 1 takes into account that I've already calculated the mean value. So it's subtracting the fact that I already have 1 data point associated with the mean value. So what's the other question?
I don't know if you are going towards that direction. Is there a direct relationship between collected data and the Gaussian distribution?
Is there a direct correlation?
Yeah, direct relationship is a question, but yeah, I would say correlation.
Yeah, that's a good point. So it turns out that most data that we can, essentially any data that you can randomly sample, in the long limit of high statistics, it will start looking like a Gaussian distribution. Not everything satisfies a Gaussian distribution, but every randomly sampled distribution will end up looking like a Gaussian distribution. And it's going to be centered, meaning if I sample randomly some property, it's going to lead, the average value of that distribution is going to coincide with the mean, the most likely value, and then I'll have some standard deviation that is associated with 60% of that sample. And so Gaussian distributions become remarkably important in data analysis. There's going to be more refinement tools later on, the more and more sophisticated you start becoming with data analysis, that not all distributions are Gaussian. And so you might have distributions where you can have let's say a shallow peak and not so a steep peak on this side, and then it might have a long tail. And so then, let me actually go to the iPad. Yeah, it's a great question. And it's...
Raúl, sorry.
Yeah.
a very nice question. I think that it's important to attach it now. It's very fundamental in physics. Is the following: how strongly statistics and probability data analysis are needed in statistical mechanics?
Do you want to go into that?
I would prefer you to go.
Sounds good. Let me first I'm trying to connect my iPad again. It disconnected. Weird. Oh, there we go. Good. And so the question about distribution. So not every single distribution is going to be Gaussian. And so sometimes you will have, so a Gaussian distribution, you've already seen it, right? It looks like this. It's peaked around the middle. And, you know, the standard deviation tells you where 60% of the data lies, right? But sometimes your data might look something like, you know, you can always calculate the distribution, right? And not always, you know, you don't have to have, you don't always have to approximate your data as a Gaussian distribution. Sometimes you can do more sophisticated analysis, and we're not going to touch on that. And in fact, I mean, I'll admit my limitations. Like I'm not a statistician. This course is not supposed to give you any, you know, strong information about data analysis at all levels. This is just trying to get you to the point where, like, you know, can understand the basics and build off of it. Okay. But let's say that you had a distribution like this, right? If I were to then calculate the mean value, well, you might say, oh, is that coincide with a peak? Well, the answer is no, right? Because you have points way off here. And so your peak, your average might look something closer to here. It's going to be skewed from the peak. So the average is going to tell you, you know, what is the average, let's say, mass of this distribution, but it's not going to coincide with the most likely outcome, right? So the mean and the median are going to be off of each other. The mean is going to be here, while the median is going to be over here, okay? But for all intents and purposes here, we can start assuming that we're going to be thinking about distributions that are just Gaussian. That's sufficient for now. And once you understand this, and once you start understanding into, you know, applying to data, much later on, you can start refining your understanding of data analysis. On to the question of statistics and statistical mechanics. Is that what was the question about? Yeah?
Yes.
Okay, good. So I mean, the basis of statistical mechanics is to think about, in some fields of physics, we focus on the interactions between two particles, or perhaps three particles if you're bold enough. And in fact, a lot of my research these days is trying to understand three-particle systems. And Connor, who's in the call, is working. Connor McCarthy and others are working with me on this, which is trying to understand quantum mechanically, how do you describe the dynamics of three particles? Well, what happens now if you have hundreds of particles, like in gases or liquids? Now, starting to think about individual particles and their position in spaces starts to become a senseless question. So what you then start to do is trying to essentially average over the dynamics and kinematics of these systems. And so you start to now make descriptions of the bulk properties of the system rather than individual particles. And that's the basis of statistical mechanics. How is that tied to this? I think that's kind of outside of the scope of this class, but that's the basis of statistical mechanics, which we're not really going to touch on much or at all, essentially. The closest thing that is going to be related to statistical mechanics is that we're going to talk about how spin systems work towards the end of the class. We're going to talk about the famous Ising model, and we're going to start coding up some simple examples of trying to understand basic properties of Ising-like systems. But we're not going to talk about statistical mechanics. Okay, can we maybe move on from there? Okay, so we did this simple exercise. Now let me just summarize the tools that I just showed you in Python. And what we're going to do now is that we're going to start introducing a problem. And this is an exercise, and I think this would be perhaps a good stopping point for this problem, or for me to lecture, and then we can start trying to get you get involved and trying to basically put these ideas into practice. And so I already told you that numpy.mean is a function that calculates the average and the mean. You can define your own functions, but you have it already built into numpy, so we might as well make use of it. Numpy.standard deviation calculates the standard deviation of an array, but in fact, sometimes you might want to have different subtraction points of n. This doesn't really matter for the scope of this class, so you can just fix that to 1. For plotting, we've already used matplotlib, but if you import matplotlib, then inside of it you can also plot histogram distributions. And so what I would encourage you to do right now is just open up your Python and put some of these functions to practice, right? And so let's say, and so what this does is that it plots the distribution of x for n bins. So meaning n is some number of bins that that are going to be set for you. So let's say that my distribution, let's make it a silly one. Well, actually, no, let's not make it a silly one. Here are, let me not skip ahead. Let me use this function right here. Let me import p random. Good. So here's another function that you're going to use in just a second, which is inside of numpy, there's another library called random, and inside of random, there's a function called random. And what this does is that it generates numbers between 0 and 1 that are randomly distributed. And so here's an output. And I'll tell you why you're going to be using this in a second. You're essentially going to be using this to calculate pi in just a second. And so here you see that every single time I call random, this function, and I tell it to give me 10 random numbers, you see these numbers look different than the previous ones. And so I can do this any number of times. And every single time I get different numbers, okay? So let me, instead of 10, let me do 100. And so now you're starting to see numbers that are randomly distributed from 0 to 1, and there's 100 of them. So now let me make that my x. Let me make x is these 100 randomly distributed points. And next, let me play with this histogram function. Let me separate these into 10 bins, and I'm going to plot x. And if I look at it, this is what I get. And in fact, in IPython, if I call this function again, it's going to pick another color and just plot right on top of it. And so here I just plotted it again, but this is because I just asked for the same axis. Let me change the value of x and now plot it one more time. And you see, again, I have 100 points. And in fact, if I were to tally the number of bins, so they separated into 10 bins. And so if I were to tally the height of the bins, so 14, 7, and so forth, this has to add up to 100. And so let's do something more fun. Let's make this now not 100, but rather 10,000. Let me try that again. PLT. You see now the height got increased, right? And the point is that because I'm randomly distributing it, the probability of me picking a number between 0 and 0.1 is essentially equal, and eventually is going to be equal to the probability of me picking a number between 0.8 and 0.9. And so we can see that the more numbers I pick, let's pick x to be not 10,000, but let's do 1,000,000. then the height is gonna increase, but also the probability is gonna become more uniform. Because these are randomly distributed, right? I'm randomly picking numbers in all of this. And so the difference of the height becomes minuscule compared to the height of each one. Okay? So this is a function that we're gonna be using in the next exercise. And so what's that exercise? I've already alluded to it enough. Let's just get started. So what you're gonna do, your first problem is to calculate pi. And you're gonna statistically calculate pi. So how are we gonna do this? Well, hopefully you already know that the area of a circle is equal to pi r squared. Hopefully. Where r is the radius of the circle. And so we're gonna use random numbers to determine what pi is. And here is how you're gonna do this. First, you're gonna generate a random set of points of x that are inside of this constrained box, where x and y, both the absolute value of them, are within 1. Okay? And then you're gonna calculate the distance. Here, let me use the iPad. The iPad is gonna be easier here. So this is what we're gonna do. You're gonna pick random points and then categorize them. And so if a point, what color did I pick? I used blue for inside the circle, good. So here's my blue. So if I pick some random number for x and y, and if it's within the circle, and the circle is defined so that this is x, this is y, this is when y is equal to 1, this is when x is equal to 1, this is when x is equal to -1, this is when y is equal to -1. Okay? And the radius of the circle, obviously, is equal to 1. So r is equal to 1. And so if x, so let's say this is x naught plus y naught. So if x naught plus y naught square is less than 1, less than or equal, well, let's make it just less than 1, is within the circle, in circle. Otherwise, if x naught plus y naught is greater than or equal to 1, we're going to call this out of circle. And the equal condition doesn't really matter for this point, for this exercise. And so if it's inside of the circle, we're going to label these as blue in my picture. And so they're going to land somewhere in between. It's random, right? And then if it's outside of the circle, but inside of the square, we're going to make that red. Okay? That's the idea. And the point is that the probability of me being blue is just equal to the number of blue points divided by the total number of points. But this probability is equal to the area of the circle divided by the area of the square. But the area of the square is equal to, the area of the circle is equal to pi r squared. The area of the square is equal to pi r, 2r, sorry, because this length right here is equal to 2r, and r is equal to 1, so that's equal to 2. And so the point is that this number right here on the left, which you can calculate statistically, is directly related to pi. And so the equation we're going to be using is this. Pi is equal to 4 times the number of blue points divided by the total number of points. And so you have to calculate. That's the goal. Oh, sorry, my computer just went to sleep. All right, good. Is that clear to to at least the TAs? What the goal is?
Very.
Yep.
All right, cool. And so you're going to calculate random numbers between x of x and y that are less than 1. Then you're going to calculate, you're going to shift them. So there's a code for you to calculate random numbers from 0 to 1. And then you shift them so that they're centered around 0. And the height is 1. The maximum value that it can take is 1, and the minimum is -1. So this does that shift for you. And this calculates r for you. So you take x squared plus y squared, and you take the square root. Okay? And so then the next tricky thing is that if you have to calculate this, right? If r is greater than 1, we're going to label it as red. If it's less than 1, it's going to be blue. Okay? And I get, like I said, the equality doesn't really matter here. You can set it equal. You can say greater than or equal is going to be red, or less than or equal is going to be blue. Whatever you want. It doesn't matter. And then you're going to use this formula, which we just calculated. And so you're going to calculate these numbers and then solve for pi. And so what I expect you to do, I'm showing you some useful tricks for how to do this. But with everything, with physics, with programming, it's useful that you solve the problems however you want. We want to encourage creativity. And so if you find a better way to solve this than me, wonderful. I assume you will, because there's always better ways to solve things than the way that I do them. Okay? And so here is a result of my code, which I've already shared with you. I've already put it on the Dropbox. You can access it if you want it. And so this is what my code shows. So I labeled some points in blue, the ones inside of the circle, and the ones outside in red. And so you see this distribution. And here I'm showing you the value of pi that I get as a function of the number of points that I've calculated. So here I calculated with 100, here I calculated with 10,000, with 1,000,000, and so forth. And so this is the number one issue, is trying to calculate pi. And so you see that my distribution is, my number of points is kind of random, but then it starts to add my mean value of pi, which is 3.14, blah, 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 blah. Okay? If this is too easy for you, good for you. Let's give you more challenges. Here's some extra challenges. Estimate the error made as a function of the numbers of points that you've used. What is my error for 100 points, right? You see that, this is really far from my value, right? Can I estimate that error? What if I use, here it seems like it's very close to the real answer. What is my error there? So estimate that error. And I'll give you some ideas, or just do it however you want. Second, plot the histogram for the largest value considered into 30 bins. Show that the distribution is centered around the average value, and the one standard deviation includes most of the points of the distribution. So this is testing whether you can make histograms, whether you can do mean values and standard deviations, and convince yourself that you should be able, that these coincide. Write down your mean and standard deviation functions. Check that you agree with the one in NumPy. So do your own checks, okay? And then here's an extra challenge, extra challenge. Write down code that will give you pi to a desired level of accuracy, and plot how long your code takes as a function of the desired accuracy. So if I ask you, I want eight significant figures, right? How long does your code, can you write a code that gives me 8 significant figures? And how long does your code take to calculate those 8 significant figures? And so forth, okay? And so this is what I expect. This is the kind of plots that I expect that I've calculated. And so here you see, this is already showed you. Here I'm showing not just the mean value, but also the little error for the maximum for a large number from a largest point, I think. Here is my error for, instead of just showing you one point, I'm also showing you the error that I estimated by just calculating the same quantity randomly over and over again using different samples. And so I've resampled pi for 100 points, and you see I'm getting an estimate of my error. And the error is decreasing the more points I have, which makes sense, right? That's what you expect. The more points I have here, the smaller the error I should get, okay? And here is exactly what I was asking. I was asking you to make a distribution of the points that you're getting for the maximum value of points that you're obtaining. And so you see that my average is, somewhere close to the actual value of pi. And I have here's my mean value right here. Here's my mean value for standard deviation, mean value minus standard deviation over here. Okay, so I think that's a good stopping point. And so I'll wait to see if there's any questions out there. In the meantime, I can maybe tell you what we're going to see next time. So on Thursday, we'll start talking about decay processes in the standard model. And we're going to do a little bit of fake data analysis where I'm going to give you the distribution associated with one decay, and you're going to have to determine the mass of the missing particle in that decay process. And so it's going to be tied to neutrino decays. So do we have any questions out there that we can try to answer?
Programming oriented questions, such as Tejus from Virginia asks, what is an array compared to a list? So a list is appendable. You can add items to a list. However, when passing a list through mathematical functions, it doesn't quite like operating with other mathematical functions. So you'd use an array if you need to let's say multiply every item of your array by a scalar number or add a number to it. But if you want to physically make your array longer, you'd rather want to do that with a list instead.
Something like this. That's what you mean, right? That we can append. So there's different, they're closely related and they have like different different abilities. And so maybe the number one thing is that list doesn't have to be of just numbers. So I can put question asked. I don't think this should break. So I've made my list. In this case was up to this point. You see, I started. Let me start again. So let me call IPython. PyLab. So I call IPython PyLab so that it built in NumPy. So here's X. It's empty. I define X to be a list by making it X equals an empty set. Okay, and so you can check that it's a list because if you type type of X, then it's a list. So let me make here an array. Let me make Y an array of 1. Okay, and so if instead I type on Y, it's going to give me a NumPy and the array. Okay, so the advantage of it is that I can, as Alex was saying, I can append to it a number. So let me append to it 1. And so what it does is that it stacks up 1 to the right-hand side of it. So let me instead append 2. Well, what should X be now? X has been, before it was 1, so I appended 1. Now I'm appending 2, so it's going to be a list with 1 and then 2. But then I can also append not just numbers, but I can append strings, like question asked right here. So this is a string. And so if I then print X, it's going to be, the first element is going to be integer. The second one is an integer. Actually, I think this is a float. And then it's going to be a string. And so list allows you to have different objects built in together, but there's some limitations in how you treat them. Arrays, if I do X, it's an array, okay? Let me make this instead of Y. Let me make Y0 is equal to, let me make this a number that starts with, is a A range, so it starts from 0 all the way to 10 minus 1, okay? Now let me make Y1 to be equal to A range of 10 again, but instead I'm going to shift them all by 1. So there's one power that arrays have, is that if I grab an array and I add to it 1, it goes element by element, and that's 1, okay? And then also I can add Y0 and Y1 together, and it adds element by element. So you see I get 1 plus 0 is equal to 1. 2 plus 1 is equal to 3, and so forth and so forth. I can also do arithmetic manipulations, not just adding and subtracting, but also I can take products. I can also take powers. And so it will go element by element, multiply times 2, and then square it, and then add it to Y0. And so arrays are really powerful and very useful. And in fact, my code, which you should be able to see on the Dropbox folder, so just to remind you, so if you go to the Dropbox folder, you see project 3. Here is data that you're going to have to analyze for Thursday's exercise. But if you go to my code for CalcPy, essentially my code is relatively short, and it manipulates arrays. So this numpy.random function that I called earlier on, it creates an array for you. And so I define my function of CalcPy to be a function of the number of elements that I want my array to be. So I would encourage you to use arrays in this exercise. And as always, I put a lot of comments in here, explaining what my code does and, what are some of the steps that are less clear that I take. Any other questions out there?
Yeah, we have a question from Javier Salgado from Mexico. He asks, can you explain how does the second argument of the std function work? I think the second argument,
yeah. So that I defined over here. Sorry, I'm trying to find my mouse. So here, in general, if you have numpy std x, comma, so if you don't use this, I think the default is going to be n equals 0. Can't remember, but you can check that. Huh?
That is the default. You're correct.
Yeah, okay. So, and so if you calculate if you set this n equals to any number, is going to just scale that by n over here. And so it's just a freedom that is built into the standard deviation function. Any other questions about that or anything else?
Someone asked, it was Francisco Mina from Mexico, if arrays can be treated as matrices.
Yeah, so you can have matrices that are, yeah, that's a great question. Let's say, let me make a matrix that is a 2 by 2 zeros, is a 2 by 2 matrix of zeros. And so this is an example of that. So if you do in NumPy, there's a function called zeros, and it gives you the default definition is you give parentheses, the number of columns, and then the number of rows. So 2 on one side, 2 on the other. And then you can specify the type. It could be float. It could be also complex. And so this gives me an array that is 2 by 2 of zeros. And so let me call this X. Okay. Now let me make another one that is not of zeros, but rather of ones. And so let's call this one Y. And so you can guess it is ones. And so here is X, here is Y. And so if I grab the 0 component, I can grab the 0 component of X, and it's going to give me, so you're grabbing the, I think you're grabbing this component right here. So you're grabbing the first row, and then you can grab the 0 component of that, and you have it 2 different ways. You can either do it by 0, 0, or you can grab the 0 component of 0 this way. Either way it would work. Okay, and so I can grab, just like with one-dimensional arrays, I can add 0. I can add X and Y, and so I have just add zeros. Each component, I'll grab a 0 and add it to a 1 and so forth. And so I just have a 1 by 1. I can also multiply this times 2, right? I can multiply the zeros by 2. Doesn't change the answer, of course. And then there's other matrices that you can always generate an array that is 2 by 2. Here's the notation. And so this oh no, okay. I need to think about what is the notation to create. I think you always have to start with, I usually start with zeros like this. So this definitely, but okay. Now you know, at least this gives you an array that you can create that is, empty, and then you can fill it in with whatever you want. But you can definitely, and then you can do manipulations between matrices, like taking dot products, adding them, and so forth. Taking determinants, inverting them, all the basic tools that you can use on that, all the manipulations that you want to use on matrices, you can do in here as well. Meaning you can do it on, you can apply them on arrays. So I see we have a question on the Slack. Should we use random values we get from Python functions for the X and Y, or the ones we multiply and subtracted from? So the function that I gave you, so there's many different functions, and in fact there's random distribution functions that you can do. So random library in Python. So I just put in Google random library in Python. And so here you have different functions that are already built in for generating random numbers of different choices and different types. And so here I'm using the function random. But in fact, you could use another function, which is uniform, which returns a random floating point number between A and B. And so if you want to make your life easy, you don't have to use this function. This function is just defined to be between 0 and 1. And then I proceeded to make a shift to it. If you want to use a different random function that, another function that generates random numbers, let's say from -1 to 1, you can just use this, and then you don't have to shift anything. So I'm not telling you how to solve the problem. I just gave you one possible way to get at it. The problem is really, you need to generate numbers that are inside of this box, and then sort them, right? So let's write some flowchart, some pseudocode, some flowchart how you would calculate this, right? So you will have so you would enumerate the, you would label the points into X be in, so X blue and Y blue, and then X red and Y red. But all you need to know, so these are all the possible points in X, they're X and Y coordinates that are inside of blue, and then those that are in red, right? All I need to know is the total number in blue. And so once you've gone through a list, you can imagine doing a for loop for I0. Let's make this bigger. For I in range NT, let's say. So NT is the total number of points that you want. You would get a random, oh my God, random value X naught and Y naught, okay? If X naught plus squared, these are bounded, so both of them are bounded to be inside of the box, right? So that means that they have to be greater than -1, but less than 1. If this is less, if x naught squared plus y naught squared is which is the radius, right? If it's less than 1, that means that the ith element gets added. I is added to blue points, right? And obviously, if not, else, then I is added to red points. Okay? And so hopefully you can read my chicken scratch, and if not, I apologize. I may not be a medical doctor, but sure, write us one. Okay? So otherwise, I is added to the red points, okay? And so then you have to enumerate the number of red points and the number of blue points. And then once you've done that, so here, in fact, you can just write it into, in fact, you don't even need to add anything into the red points because you already have the number, the total number of points, which is NT, is your input into your function. And so all you have to do is just count the number of blue points. Sorry, okay? And so all you need to know is just a number of blue points. Once you have the number of blue points, then pi is just equal to 4 NB divided by NT, and you're done. The problem, though, is depending on how you write this for loop or this if statement, it could scale differently with time. Some routines are faster than others. But I think this should help with trying to assort, to figure out the problem. And also, depending on how you generate your points, right? Get a random value. This is another place where there could be a bottleneck as far as time goes. Okay? Do we have any other questions that we should maybe address? Is Juan on the call? Do we have any Spanish questions, Juan? Juan, do you want to maybe go to another session and answer some questions in Spanish?
So far, no questions in Spanish.
Okay.
There have been several questions. I mean, you already pointed out that the denominator in the standard deviation is n-1 because we have 1 degree of freedom.
Right.
However, some of the students, for example, Claudia Diaz from Mexico, she asked, how can we know exactly that we have 1 degree of freedom? And Lucas from Brazil asking why we use lowercase n equal 1 instead of other number. So this is something that depends specifically in each problem, but I don't know if you want to point another example or... Because, I mean,
Sorry, what was that?
I mean, the fact that we have 1 degree of freedom is something that depends on each problem, but I don't know if you want to, if you have another example in mind or...
No, I really don't. And I mean, so the standard deviation, it depends on the context that we defined it. So sometimes you might want to take the standard deviation of the mean, the standard deviation of the distribution. And so these all have peculiar, and perhaps the most accurate definition in this case would have been to not have the n-1. If we have a random samples, I think that might have been the most accurate definition. In the large limit of points, either one doesn't really matter, right? It's the deviation is gonna be small between one or the other. And so let me double check that we're using the correct definition in this case. But there are other definitions of standard deviations that are whether you might have a unbiased or biased distribution sample of your distribution where you have to modify the denominator, and so that's why there's a built-in freedom into Python. So it could be that I've made a mistake, so I'll double check, make sure that the one that we want to use for this case is with n-1. If that hopefully maybe clarifies any confusion that has been out there.
We also have a question from Simeon Petzolik from Cleveland, Ohio. He asks, how can I unmute inline plotting in Spider? And the way you go about doing that is that at the top left of Spider, you should see your file, edit, search tabs, all that. Go to Tools, and under Tools, you're going to hit Preferences. Within Preferences, hold on, my one's loading up. Yeah, within Preferences, you hit the IPython console. And within the IPython console, you hit Graphics. And under the Graphics backend, you can select inline instead of automatic.
Do you want to do a little demo of that?
Yeah, I can definitely do that.
Okay.
Share screen. Can everyone see my screen?
Yep.
So at the top here, you go to Tools, and at Tools you'll find Preferences. Once you click that, it takes a second on my computer. You should see a window pop up. Does everyone see this window?
Yeah.
Small Preferences window. Yep. Good. Within the smaller Preferences window, you go down to IPython console. It's about halfway down the list. And then you go to Graphics. And under the Graphics backend here, you just select inline as opposed to any other setting you might have. Simple as that. Hit Apply. Okay, and you should be good to go.
Great. Any other questions out there? hopefully it's clear the problem that you guys have at hand. As I said earlier, if you want to start sharing code with us, what you can do is just email us with Dropbox access. And so I need to add your email I need to have your permission to write your email, to add your email to the Dropbox folder that we're going to be sharing. And it's going to be this one, Students, Python for Physics 2020. And what I'm going to ask of you, you make a folder like this that has your first name and then last name. Okay, so let me use myself as an example. So you're going to write Raul. Don't write Raul. Write your name, okay? Underscore, and then your last name. Okay, so here's mine as a student. And so right now there's nobody else because I haven't checked my email folder just yet. But if you want to be added here so that you can easily share your code to us, just write to us at this email with the subject line, okay? Any last minute questions or anything that you guys want to address since we're close to running out of time?
Yeah, real quick. We had a question from Max Hanrahan from Erie, Pennsylvania. How do you plot blue and red points?
Good. So in my code, the function that I use is called error bar. There's other ways to plot points, but I use the function error bar, and you have it in the example. So I essentially created the examples that. Let me try to clean up this. I created the examples in the first, in the example 0, so this is Python for, so in the project 0, I created 2 examples, and in it you generated figures like this one, right? And there you have, I've designed this so that you have ways to code already built in that you can use for plotting things in blue and red, and creating these little points, this little error bar points in blue and red, or squares in blue. And so I've actually used the same code here for doing that. So I use error bar, and I make the format type, I think is what this is a 0, which means circle. The color is red. And then these are other specificities, but you don't need those. So you can just use, let's say, error bar. So you import from matplotlib, error bar function. Let me plot 0, 0. So it's going to give me a point at 0. FMT is going to be the type. Let's make that a square. Sure. And then color, I can make it whatever I want. I can make it red. And so what I get is this 1 point at 0, 0, and it's red. Let me make another point. Let's make it orange for some fun. Let's make it a diamond, and let's make it at 0, 1. As you see, at 0, 1, I have an orange point. And then I can just, can I plot maybe? I think I define X. Oh no, that's gonna, let me do a range 10, a range 10. So this takes arrays, as long as they're the same size, you can put them, okay? And in fact, here, let's put error bars, because this function suggests it is error bars. So let me introduce a X error. And I'm going to make this equal to, it has to be the same dimensions as the points of error. So let's make it a range. Let's make it ones of just ones that are 10 ones. Okay. Whoop. Oh, I think it's not error. I think it's X. Yep. There we go. You see, I've added X errors along the X-axis. Now let me add errors along the Y-axis. Same thing. Boop. And it looks kind of funky because I've made let's make it a little different. Let me make them instead of size 1. Let me make them to be 1/2. Oh, let's make it 1/3 actually. So I'm just going to divide these numbers by 1/3. And because arrays work so that I can add any arithmetic behavior to each individual component of the array, this just divides all the components by 3. So it gives me 1/3. Look at that. Look how pretty it is. So it's starting to look like data, right? All right, so if you forget this stuff, it's already, it's built into one of the examples. I have used the error bar function, and then in example 2.3, I even did histograms because I knew that we were going to do these kinds of problems. So I built in quite a few functions already for you here for you to play around. I mean, they're already built in NumPy or in Matplotlib and NumPy, but I wanted to point you to them. So if you, these functions that we built in the first exercises might turn out to be useful now. Any other questions out there?
Yeah, real quick. There was a question a little while ago, actually, by Natalie in Talia in Virginia, which asked, how can you get a matrix where the numbers are not all only ones or zeros?
Okay. So, well, okay. So one easy way is that there's different ways of doing this, but let's say X is 0. I've defined this to be a matrix of zeros, right? Well, what you can do is that I can grab each element of the matrix and replace it with whatever number I want. So I can identify this to be, let's make this 1. So let's look at X again, okay? I grab the 0 component, the 0, 0 component of X, and I set it equal to 1 now, right? So now let me print X. I see that X now, the 0, 0, so that would be this is the 0 component, and then the 0 component of 0 is this one. And so I've set that to 1, okay? Now let's make this is where I sometimes get confused. So let me make the 0, 1 component of X equal to 2. Ah, okay, good. My logic worked. Okay, good. I was worried that it was going to be this guy, but no. Okay, good. So then this grabs the 0 component of X, and then I grab the 1 component of the 0 component, and then turn that into a 2. So now I have this is 2, right? Great. Now let's do that for the 1, 0 component, and I'm going to make that, you guessed it, a 3. And I'm going to grab the 1, 1 component and make it a, everybody, 4. Wonderful. Good job. And so this makes a matrix of 1, 2, 3, 4. And so you can populate, and if you let's say that I make, let's make A X to be, you might ask, okay, how do I do this in general, right? Well, in general, you're going to write code, right? So here's a matrix that is, let's make it 100 by 100, right? And so then I can write a code that is for I0, for I in range 100, for J in range 100, X, I, j is equal to, what do you guys want to make it? Let's make it I times j. Why not? And so here's a matrix. I can't really look at it now. I can I can plot, let's say we can plot, what do I want to do? Oh, crap. Sorry, I got caught up there. So I can plot, is there any way to visualize this? But basically, there's a matrix whose element now I and j are equal to I times j. And some important things to check, right, is that, let's say, this should be symmetric, right? And so we can check. Let's do 1, 0 should be 1 times 0. Good. Or I mean, 1, 2 should be 1 times 2. So that makes sense. And 2, 1 should be 2 times 1. Great. We can make this 10 times 10. Should be 100, right? 10 times 11, 110. Even I can do that. 11 times 10, also 110. Great. And so this is one way that you can start writing genericized matrices that then you can fill in with, some algorithm, and then you can proceed to manipulate them. And in fact, some of the research that we're doing, for example, with Connor, involves using matrices that are in thousands of elements and manipulating them. In some other cases, we're using even larger matrices. So matrices are remarkably powerful in physics in general. So it looks like we should probably wrap up. And so, as always, go to send us your emails. If you have any comments, suggestions, send us an email in Python for Physics. Also, there's a handy dandy survey that you should fill out where you can give us feedback, see if we're doing a good job. It's always appreciated to figure out if we're doing a good job or should do a better job. Whatever concerns specifically you have about what we're doing or what you want to see, send it to us. And then also, please send me, if you want to be more interactive and show off your code, send us an email here with the subject line being Dropbox access, and then we'll give you access to it. And with that, let me turn you to the next program, which you should be able to see. And let me say, this is a program that I'm really excited about, which is one of our first panels on diversity in STEM. This has been so there's going to be different panelists, including Alan Mecca, who's one of the team leaders in REYES, as well as Orlando Ayala. They're both team members of REYES, faculty. Alan is a faculty in psychology. Orlando's a faculty in mechanical engineering, technology. And then we're also going to have Holly Gaff, who is a professor in biological sciences. She, in fact, is going to give a talk soon, I can't remember exactly when, on studying ticks. Fascinating. So you should definitely join. And Debbie Waller, perhaps you've seen, she gave a talk on how to solve crimes using entomology, which is the study of insects. And so if you didn't see her talk, I would encourage you to look back. It was quite a bit of fun. And she's going to give another one later this summer. And so go to that. I think it's going to be really interesting. This is something that I'm deeply involved in, which is how do we diversify the sciences so that we best can learn from each other, right? We're seeing here in Python for Physics in this class, we have people from all over the world. And I really think that from learning how from seeing how we all try to think about problems in a different way, we can all learn quite a bit better. We all benefit from each other's diverse talents. And so that's the idea of this panel, is trying to, how do we encourage diversity and communication between different kinds of people in the sciences? So please join that. Okay. And with that, I'll see you on Thursday. Okay. Same time, same channel. I think that's the end of that. How you guys doing over there?
Good.
Good? I think we might still be live, so just in case.
Yeah, we're going to be live probably. I'm just going to let it run because I have to account for the delay in the record. I'm just going to let it run for another 2 minutes and then I'll end the actual stream.
Sounds good. Thanks, Scott. Are there any other questions that we didn't get to?
No, I think we hit all the big ones.
Okay, sounds good. How you guys doing? I didn't know when was the best time to do a breakout session. And I don't know if, what do you guys think, if it makes sense to have more breakout sessions or less? Or if it makes sense to have breakout sessions at all?
I personally like the Slack chat for answering questions. It just, we need to encourage people to send more stuff there.
Yeah. Sounds good. Yeah, I mean, I think between Slack,